Okay? So, today we continue with the next chapter, statistical inference. Inference is related directly to confidence intervals. So, we usually, in statistical inference, we usually try to have something like tests. Inference is focusing on drawing conclusions about the population. So, we try to draw these conclusions with tests. We call these statistical tests. Okay? And usually involves what is called hypothesis testing. Again, hypothesis testing is based on the previously developed confidence intervals. It uses the same distributions. Now, we cover in less than half of this chapter, because most of the stuff we'll be doing on the computer, and I'll try to focus entirely on the practical stuff. So, a hypothesis will have a null hypothesis, which is the basic stuff, and the alternative hypothesis. Examples that you can understand and relate will be null hypothesis. The scores of girls and boys are the same. And the alternative hypothesis will be, and now here's the trick, it's coming many slides down the road, two-way hypothesis. The two-way hypothesis is that the performance is different, but different in two ways. It could be that the girls' performance is higher than the boys', or it could be that the boys' performance is higher than the girls'. Both are possible and both are likely. Of course, the null hypothesis is what we expect. There is no difference. Now, I'll jump ahead and give you immediately the example that you can understand with a one-way hypothesis. In a one-way hypothesis, you check only for the one, but you don't worry about the other because it's not very likely. Example that people understand is that boys are taller than the girls. Now, the null hypothesis is that the height is the same. And the alternative is that men are taller than women. This is a one-way hypothesis because it's extremely unlikely. In the real world, we know impossible that on average, girls are taller than the boys. Okay? Now, actually, we can check and test the same hypothesis for 12-year-old boys and 12-year-old girls. And at that point, it may be true that the girls are bigger and taller than the boys for purely physiologic reasons. So, for grown-ups, we're sure the hypothesis is one way. Boys are taller than girls. But for young children, it may be true, it may not be true. For 7-year-olds, maybe the girls are bigger, maybe the boys are bigger. We need, for children, a two-way hypothesis. All right, let's see what else. The legal system, I already gave you a better example that you can understand. Again, when you test a hypothesis, exactly like with the confidence intervals, you have a level of significance. And the level of significance will be the risk of making an incorrect conclusion. Statistically, we usually use the 5%. Sometimes we could use 1% when we want to be more sure. And if it's not very important, maybe we use a 10%. Again, depends how important the problem is. For example, you got a potential drug, and drug is in a medicine. You know, pharmaceutical company manufactures the drug, and the big question is there a risk that the drug will actually damage the patient and hurt the health of the patient? Well, if there is such a risk, you want to have a high level of significance. you want to have 1% or less. You want to make sure that the drug is safe. Okay? And then there's a completely separate question, does the drug really work? So you're going to have maybe, again, it's a classroom of 40 people. You give to 20 people the drug, and you watch the result, and you give to 20 people the sugar pill, okay, meaning nothing. And you watch and see the effect, and you see if there is a statistical significance, okay? And if the drug works, there will be a difference. And if the drug doesn't work, there will not be a difference. So, the null hypothesis will be the drug is not effective, meaning doesn't work. And the alternative hypothesis is the drug is effective, it works. Well, is there a problem if we make a mistake? We could use 1%, but if we use 5%, it's not a big deal. We can even use a 10% mistake, okay? If we use a 10% level of significance, it's still okay. As long as the drug doesn't, excuse me, doesn't hurt people, then we can afford a higher mistake. Then we can afford a higher level of significance. So that's the difference that you need to understand. It's a matter of common sense. It's not a statistical question. It's a matter of business sense or common sense. If you're using a vaccine, the first big question is it going to hurt the child? And then is the second question, does it really work or it doesn't work? This is not a question of statistics, okay? Same thing with advertising. You try to do some advertising, you want to spend some money, maybe a big advertising. Again, it's a business question as opposed to statistical question. In business, common sense will determine the level of significance, not statistics. What statistics could determine later on, based on the level of significance, statistics will determine usually the sample size. Would it be enough to test on 40 people the drug, or we'll need 100 people, or maybe 300 people, okay? That's where statistics enters the game. All right, there is a one sample hypothesis test, and a one sample hypothesis test is you use only one sample and you compare it up against a constant. The constant is some sort of a number. Let's say the average height is 160 for the students. Well, it may be more than 160, it may be less. You just measure up against a certain height, okay? So you use some common sense number that you want to test for whatever the question is. Example, you have a drug which promises to lose weight, okay? So you have a whole bunch of people taking the drug, and you want to say, after 3 months of taking the drug, did people lose 10 kilograms or more? Okay. So the first question will be before is the drug efficient? When they used it, did they lose anything? In this particular case, the question is the drug effective in the sense that they lose anything more than 0? Here, we want to check, did they lose more than 10? Okay? A different way of saying it is, well, you got a whole bunch of fat people, they want to lose weight. If they lost 2 kilograms, out of 120, it's not really good. It doesn't make any sense, right? I mean, it didn't help much. I mean, it's no point in taking for 3 months a drug if you're going to lose barely 2 kilograms. It's not worth it, okay? Not worth the risk, the side effect, the cost. If you're going to lose 10 kilograms, Yes, sure, you want to do it for 3 months. And maybe for another 3 more months and lose, hopefully, 20 kilograms. So this is an example of a one sample test where you compare against a certain number. Do people lose more than 10 kilograms on average? Okay, that's a simple example that, I'm trying to give you examples which are common sense related to health, to simple things that somehow you can possibly see. So, I don't want to get into this, the proper form of a hypothesis, but basically, what you need to understand in statistics is that statistical testing gives you or provides information for rejecting the null hypothesis. It means the following, that's important to understand. When you have a certain hypothesis, if you cannot reject the null hypothesis, it doesn't mean that you prove that it's correct. Maybe it's correct, maybe it's not correct, okay? What you want to have statistically significant is the opposite. You need to design such that you want to reject the null hypothesis. Somehow you want to find the difference. If you want to find the difference, you're like 95% or 99% sure that this difference is significant. So in general, you try to look for significant, you try to look for differences, okay? And that's how we design the null hypothesis. We design the null hypothesis that you're actually finding the difference. Maybe boys are taller than the girls, maybe not. Okay, maybe the girls are taller than the boys, okay? So you want to get the statistics and reject the null hypothesis that they are equal. Now you have strong statistical evidence that they are not equal. On the other hand, if you cannot reject the difference, it didn't mean that you showed that they're equal. No, you did not show that they're equal. All you showed is that they're not different, which is not the same as saying, oh, they are equal. Okay? So that's an important point to understand. They got some example. We're going to run through examples in the lab from whatever we can do with the data. I don't want to spend any time. Okay, well, the first two, so you may have a hypothesis which is correct, and the test will not reject it, okay? Fail to reject. So, means number one and number two, everything's okay. The two main mistakes that you can commit in statistics are called type 1 error and type 2 error. Type 2 error is related that the null hypothesis is false and the test cannot reject it. Null hypothesis is false and you can't reject it. Let's see. You have the medicine, the pharmaceutical drug that people take, and the null hypothesis says that the drug does not hurt your health, okay? Is not damaging you, okay? Well, here, type 2 error means that, oh, the drug is actually damaging, but the statistical test didn't tell you that. The statistical test failed to do that. So that's a very simple common sense to say, oh, something was wrong with the test, or something was wrong with the sample, or the sample wasn't big enough. There was a problem which resulted in type 2 error, okay? So type 2 errors sometimes can be very dangerous depending on the circumstances. Of course, the same applies. They run tests on cars or motorcycles for the brakes or for safety in general. And you want to find out, is the car safe or not? Meaning, relatively safe. And the relatively safe means up to international standards. And you don't want to commit the type 2 error when the car is actually not safe, but your tests don't show it, okay? Again, you may have to wreck 100 cars or 200 cars, or, you know, have to get into an accident, actually, to see if the car is relatively safe in an actual car accident, okay? You may have to test 1,000 cars and hope that you don't commit the type 2 error. I don't want to, you know, get into the type 1 error. Again, you're going to try to do a lot of practical examples where you can get to feel, because that's, again, just abstract theory, but that's an important concept to understand. Let's see what else we got. Okay, well, the probability of making type 1 error, that's the level of significance. This is what we typically determine. That's the, let's say, 5% or 10%. Okay, that's the 5% or 10%. And then the probability of making a type 2 error is called the power of the test. So the type 1 error is determined by the alpha, which is the confidence level that we discussed last time. It's exactly the same concept. Its meaning is the same. It is the same interpretation. And here in statistical testing, it's used in exactly the same way. Okay? And you got a power of the test, and the power of the test partially relates to the level of significance. So, if you want to improve the one, we say that there is a trade-off between the two. If you want to improve and reduce the one error, you will somehow increase the chance of the other error. So, there is a general trade-off between the one error and the other error. The only way to reduce the one error is that you will have to take the risk of increasing the other error. You can't improve both at the same time. The only way is by increasing the sample size. Okay? So, it's important to understand what is the business and economic or health, social meaning of the one error, what is the social or economic business meaning of the other error, determine which error is more important and which error is less important, and design, meaning determine whether you're going to use a relatively high alpha or relatively low alpha. In other words, whether type 1 error is more important or whether type 2 error is more important, so that you minimize the risk of the important one. And of course, if you somehow say, well, but it's really both are important at the same time, then you can reduce both by having a larger and larger sample size, which will cost you more time and more money. Let's see. Well, here they give you a simple, well, whatever it is, less than 25 minutes or more than 25 minutes. We're going to have some of these tests coming up in examples. Let's see what else we got. This is the same. Okay. All right, how do we improve the power of a test? Okay, we'd like the power of the test to be high enough to allow us to make a valid conclusion. It is very sensitive to sample size. I already explained that. We need to raise the sample size. Okay. Or by relaxing the other type of error. Now, you may, the test statistic will be working exactly like the confidence intervals. And again, you will be getting sample test, if sigma is known, you'll be getting the standard Z statistic. So if you know the variance, the distribution will be normal, and you use, this is called standard normal distribution. And the Z statistic is directly related for each observation to the Z score. So whenever you calculate for each observation the Z score or the Z value, you did that in the lab last time, right? A few times, right? That same Z score is, this Z statistic is determined from that Z score. They are related to each other. Okay? And if you don't know the variance, it will be then a t-distribution. As I explained last time, for small samples, there is a relatively large difference. For large samples, these Z and t distribution are pretty much the same. They give you some example. I'm going to try to run those examples in the lab. And then you need to make a conclusion, meaning a statistical conclusion. And statistical conclusion is either you can reject the null hypothesis and you'll have to accept the alternative, or you cannot reject the null hypothesis. And I got rejection regions. The rejection region is dependent on the alpha. If you have a very small alpha, the rejection region will be on the left. The alpha is this area which is colored over here to the left in this particular case, and that's called the rejection region. And for the right side, on the other side, it's called upper one-tailed test is here. This one is lower one-tailed test. And this one is a two-tailed test. Okay? So here you take the alpha, here you take the alpha, and here you take alpha over 2. So this is half, and this is half. So a half and a half on each side. When you add 1/2 and 1/2 will give you alpha. So each of these has a level of significance alpha, and this one is alpha. But you take only half on each side. That's how it works. Again, in the lab, it's going to see. It's actually, there is a simpler, easier, and better way. It's coming. Hopefully I'll have the time. But it's quite a few slides down the road with the p-value. P-value is the probability value of making a mistake. If the p-value is 1%, it means that we're likely to reject the null hypothesis with the risk of making a mistake of 1%. If the p-value is large, like 10% or 15 or 25%, then we do not reject the null hypothesis. I'll probably get into that. Okay, they're looking here at some example. Again, I've got to be skipping the examples to well test. Okay, the p-value is the probability of obtaining a test statistical value equal, more extreme, depends on sample size hypothesis. Basically, yeah, that's not a very good explanation. The p-value tells you the probability of making a mistake, okay? So, if the p-value is 10 or 15%, that's a very high mistake. You basically cannot reject the null hypothesis. A p-value of, let's say, 0.001, meaning 0.1%, is almost sure, like 99.9% sure, that the difference is significant. Now, let me try to just remind, for those of you who were paying attention in the last time, when we did the SAT for the college test, remember the colleges, you had universities, and the other one was liberal arts. The SAT for the one was, I don't know, 612. For the other one was 604. I'm kind of like making the numbers very close. And the p-value was 0.24, which is the same as 24%. The difference here is very small, and we say that the difference is insignificant. Okay. Now, for the cost, the one university was, does anyone remember the numbers? Like 19 or 22,000? 22,000. And for the other one was 39,000. Okay. And the p-value was like 0.01, which is like 0.1%. Here, the difference is not significant, and here, the difference is highly significant. So, even though this university is twice more expensive, it's not able to attract students with higher SAT. Okay? So, the overall performance of the admission is the same, even though this university is twice more expensive. So, the university is more expensive, but it's not more selective. There's actually possibility, not probable, that the more expensive university will be selecting lower scores. Okay? Again, it's possible, it's not probable, but we can test for that. Okay? All right, let's see what else we got. Well, again, it says reject the null hypothesis if the p-value is alpha. So, if alpha equals 5%, which is 0.05, you reject the null hypothesis. Here, cannot reject the null hypothesis. Here, reject the null hypothesis. Okay? It is that simple. In other words, a very small p-value is highly significant and a large value is insignificant. The logic is the opposite. Let's see what we have here. One-tail test, two-tail test. You don't need to find those p-values. The software gives them for you every time. They're automatically calculated. You don't have to worry with formulas or anything like that. I mean, that's a little bit of the advantage of the SPSS software, that a lot of this stuff is calculated up front for you. You don't have to worry about the different functions and whatever and all those details. Everything just, you know, gives you the result. You need to know how to interpret the result. Again, here they give you the example of, oh, the p-value is 14.9%. Well, you cannot reject the null hypothesis, or this is an extremely low number, 1%. You can reject the null hypothesis, and that's probably one of the most important things that we need to remember, one of the few things you need to memorize so that you can use it with, because all the tests will eventually be coming up with a p-value. So basically look up the p-value and see what it is. Let's see what else we got. One sample test for proportions. Yes, you can also do for proportions. Now, with proportions, things are a little trickier. With proportions, there is an exact formula, but we don't have in PSPP test for proportions. When you don't have a test for proportions, the PSPP gives you an option to do something which is very, very, very close to proportion, and for a large sample, it turns out to be identical. Camera, we need to look over here a little bit. So, it works like this. So, you have certain numbers. Here is the number, and here is male, male, female, female, male, male, female. So, one simple trick which we've seen before already in our data is we're going to convert the randomly, doesn't matter, only one. The male we convert to 0, and the female we convert to 1. The male we convert to 0, and the female we convert to 1. That's simple. It's done automatically. It's called an automatic recode. It takes about a minute to learn. And now with zeros and ones, you can take the proportion. The mean, if it's 0.37, if the mean is 0.37, this means that you have 37% will be ones. This means that the females are 37% and the males are 63%. Okay? And now comes the next part. This little mean is calculated for you by the software. Well, guess what? We already did. This little mean will also give you the confidence interval. And the software will give you the confidence interval. I'm just picking a number from 0.3 to 0.44. Okay? So this is the range. The range is from 30% to 44%. So if you need to run a statistical test and say, oh, is the difference more than 20? The answer is yes, more than 20. Okay? Obvious, because it's between 30 and 44. Then you ask, is the difference more than 25? Yes, we reject. Is the difference more than 30? Cannot reject. 35? Cannot reject. 40? Cannot reject. So, it comes like this. This is 0, this is 1, this is 30, this is 44. Here, you cannot reject, and here you reject, and here you reject. Very simple, very easy, very straightforward. Okay? There's absolutely nothing really fancy. But you need to recalculate, convert. If it's a ratio, if it's a proportion, one of them is 0, the other one is 1. You can do the opposite. Could we do 1 and 0, but then the numbers will change from 37 is going to become 63. Okay? It's fairly easy, fairly straightforward. All right. So that's a workaround, okay? Actually, you can calculate and see what's the mistake. I was calculating, the mistake is less than 1%. So if the calculation there says 30 to 44, the true number will be 31 to 43. It gives you almost the same result. Not a big deal. So one sample test for proportion, okay, continued. Two sample hypothesis test. Okay, in a one sample hypothesis test, you compare the whole sample up against the number. In a two sample hypothesis test, you compare two different samples. For example, I already gave you, we take the GPA of the girls, we take the GPA of the boys. Take the difference and see different or not different. Alternative. Take the GPA of the native people and then take the GPA of the foreigners. Again, this will be, to be honest and fair, a two-tailed test. It may be that the foreigner's GPA is higher, but it may be that it's lower. Okay? And this will be a simple example. Now, what's important to understand is the following. What's important to understand is that the two sample sizes would naturally be different. For example, natives will be 35 and foreigners will be 10. You won't expect them to be 22 and 22, okay? So that's a simple example of two samples. Now, a different example that we might actually do in class, meaning in the lab, is the following. I did on financial markets and institutions, I did your quiz, and let's say, I'm just picking a number, that the average was 65%. So students average 6.5 points out of 10. Well, that's for the second and third year students. Now, when we take the fourth year students, their average was, let's say, 4.5. Well, now the question is, well, they're lower, but is it because they're only 11 students and the exam was poorly designed? In other words, is it due to random things like, well, it was done early in the morning at 8 o'clock, they didn't have coffee, so, you know, it was bad time of the day, okay? It was poorly designed test. Or was it because the students were significantly less prepared, okay? So, a difference between 6.5 and 4.5, we can provide a test to show if the difference is significant or not. If it's significant, we can conclude the second year students are better prepared, okay? And if the significance, the difference is not significant, we say that they are equally prepared, okay? So that's a simple real-world example of comparing two means. And of course, the other one will be GPA scores, another one will be height, or any other measure that you might be interested in. Two sample tests, okay? Let's see what else we got. Usually, the hypothesis is that there is no difference. They're the same. Boys perform as girls. Boys are equally tall as girls, okay? So the two means are equal, and the alternative is they're not equal in a two-tailed test. Let's see what else we have here. Well, that's pretty much it. Let's see what else we have. Well, we have a number of variations when we make comparisons. Well, the one sample size, and the two sample test, and we know the sigma. Somehow, we may possibly know the sigma upfront, okay? We may know what's the variance of height for the whole nation, okay? Sometimes we know these information. Sometimes we'll know that the variance is the same for the one sample, for the other sample. Sometimes we don't know what's the variance. Sometimes the variance will be unknown, but we assume them equal, okay? And there is a possibility of something else, which is called a paired two-sample test. In a paired test, it means that the first result from the one sample corresponds to the first result from the second sample. The second from the first sample corresponds to the second, and every one corresponds to the same way, okay? An example of a paired sample will be the following. I will provide for you a theoretical test on the theory, and we record every student's score. And then we provide a test in the lab, and then we record the score. Well, every student will have one theory exam and then practical exam. And then we will see difference. Is there a difference between these two or not? Maybe the practical exam will be higher, maybe it will be lower. Again, maybe the performance will be the same. So this is an example of a paired test. Basically, for example, a paired test will be, well, here is the problem. Everybody do the problem on PSPP. And then here's another problem. Now everybody do the problem on Excel. And then we compare the performance of PSPP versus Excel. Okay? So that's one way to have a paired sample. You somehow have the same people observed in two different ways. Okay? Yes, in schools back home in Bulgaria, when we were in, let's say, high school, the school is relatively small, and the number of students are relatively large. So what they will do is they will have first students study in the morning. So 4th, 5th, 6th, 7th grade will study in the morning. And 8th, 9th, 10th, 11th grade will study in the afternoon. And then they will change. Okay? And then you compare the grades for the same students when you studied in the morning and when you study in the afternoon, and see if the grades are higher in the morning or higher in the afternoon, or maybe the same. Maybe, maybe not. Again, we don't know. It's the same students. Sometimes we would expect that they will be doing better in the afternoon because in the morning they're way too sleepy. Can't wake up until 11 o'clock, right? So, again, we don't know that. But that will be an example of a paired sample. Same students under two different circumstances in the compare. All right, let's see what else we got. Two sample tests or difference of means. Okay. The difference is different. Same as 0 or different from 0. We'll do that. Comparing supplier performance. We have to compare. Oh, okay. What we did in the lab with you guys or with the other group is get the Facebook friends, right? Did we do the Facebook friends? You got boys having on average 200 friends and girls having on average 150 friends. But because the samples are small, maybe the difference is significant, maybe the difference is not significant. We want to see on average, and by the same token, boys spend 6.3 hours, girls spend 6.1 hours. Is that 0.2 hours significant or not significant? Okay, these are simple, whether it's business or for example, you have a response. Let's say they do some advertising or whatever, and they want you to click, let's say on Facebook, and on average, you have 40% of boys clicking and following the link, and only 35% of girls clicking and following through the link. So a simple business question is, does this ad work better on boys and doesn't work so good on girls? Well, if it works the same, fine. But if it doesn't work so good for girls, then the next business question is, because on Facebook, on your profile, they know if you're a boy or if you're a girl. For the boys, they'll give the same advertising, but for the girls, they'll make a different ad, which they will try to test, okay, and see maybe the new advertising will work better. So this is a simple business example where you can check to see if there's a difference of response. And next, if we change the ad, whether there will be an improvement in response to advertising. No time to go? All right, well, that's good enough. I'm done with most of it. Well, a lot of this is just basic calculation. We or you are not listening too much. We'll do some quiz and then examples of these in the lab.